Hey, today I'm going to take a topic in physics. It's a chapter in NCERT known as Kinetic Theory of Gases. So, let me give a motivation into this subject. So, before talking about gases, let's talk about matter. You must have learned this in your elementary school that matter is something that occupies space and has mass. This is a very old idea and also a fundamental one that defines matter. Occupies the phrase occupies space gives some sort of idea that matter is a continuous entity. There is an entire branch of mechanics devoted to studying matter as a continuous entity known as continuum mechanics. But in this chapter, we are going to delve into the molecular nature of matter, especially gases and a little bit of solids. So, how and why did this molecular way of approaching matter arise? The answer lies from very old time periods, ancient time periods. It's a product of the thought of many thinkers and philosophers, finally accumulating into Dalton's atomic theory that changed the way humans looked into physics and chemistry altogether. Earlier, we used to say that solids are something that have a definite volume and shape. Liquids, they do have a fixed volume, but they take the shape of the vessel they are put in. They don't have a rigid shape. And gases, like, I mean, at an instant, they do have a volume, but their volume is subjective to pressure and temperature. Like, it's not a definitive volume. And of course, if the volume is not definitive, the shape is also not definitive. But when it comes to the molecular theory, we can say these differences between different states of matter based upon the arrangement of these molecules. In solids and liquids, the distance between the two molecules are kind of same. In solids, the distance vector is some sort of rigid, it's fixed. In fluid, they slide over each other in some sort of layers, like in laminar flow, but the distance almost remains same. But in gases, the distance are varying. They can be zero, they can be like far apart. I mean, it's completely random. I mean, as distance says, so is the force of attraction. In solids, the force of attraction between two molecules is kind of considerable. In gases, it's almost negligible, and it's a major assumption we are going to take in the upcoming sessions of this lecture. Liquids are some sort of medium wave, like the distance is same as solids or either medium, like, but also the forces of attraction between them are medium. So this is the idea of states of matter that arises from the molecular theory. Now let's check some opinions about Dalton's atomic theory and its implications in study of matter. So Dalton said that matter is made up of discrete molecules. Like, not Dalton, many people before Dalton also said that, but Dalton some sort of formulated it. So this gave rise to molecular theory of matter, where molecule is considered as the fundamental unit of matter. So earlier we had a continuum model of matter, where the bulk properties of matter, I haven't mentioned that before, but bulk properties were used to determine the state of the matter, like pressure, temperature, density. But all these notions do not work for molecules. Like, we cannot say like a molecule can exert a pressure. Like, you can exert a force, you can impart an impulse, but how a pressure? Like, molecules are considered to be infinitesimally small. Also temperature, like how can molecule have a temperature, or what about the gaps in between molecule, how do you assign temperature to that? So there are so many discrepancies when we come to a discrete model of matter when from a continuous model of matter. So this chapter actually deals with connecting them both using a generalized theory. But here's the catch. The issue is all molecules are not the same. Like the molecules in the oxygen, yes, is not as same as molecules in the carbon dioxide. So doesn't that defeat our purpose of a generalized property of matter? I mean, won't it be too vague? Like, would we be able to explore more? Yes, we can, and I will discuss about that later in this lecture. But let's start with some observations of Dalton, which was extrapolated into gases by Gay-Lussac's. Like reactants react in fixed ratios and create products in fixed ratios, all simple integers. So Gay-Lussac's uh, extended this to gases, and Avogadro proposed something like the number of particles in a gas is directly proportional to the volume it occupies. And that relation at fixed pressure and temperature is regardless of what the gas is. So we can formulate some sort of general theory for gases. And using that, we can somewhat patch up the relation between molecular nature and also the bulk nature. So let's delve into that. So let's get started into behavior of gases. So let me highlight two behaviors shown by gases near normal like room conditions, like not too much deviated from room conditions. Both of them are kind of obvious, but let's see. First is Boyle's law, which states that pressure and volume follows an inverse relation, kind of like PV equal to constant. All these are based on experimental findings, and according to Charles' law, I mean, if you have a piston and you are heating the gas inside the piston under constant pressure, the gas expands. So, like temperature and pressure, volume is seen to have some sort of linear relation at constant pressure. Another law is Pascal's law, where temperature and pressure have a linear relation when the volume is fixed, like a fixed container. Pressure exerted by the gas. So all these accumulate to some relation. We have PV equal to KT, where K is some constant. This relation is known as ideal gas relation. Now that constant K. So what does that K depend upon? Like, does it change with different gases, or like is it dependent upon the nature of gas? Well, it's independent of the nature of the gas. It's some kind of universal. Remember earlier, I have told according to Avogadro, the volume of occupied by a gas is proportional to the number of molecules it has. So we have here like at fixed pressure and temperature. So in this expression, if you are fixing pressure and temperature, we have V is proportional to K. So K should be a term that is directly proportional to the number of molecules. Hence, we have our ideal gas equation, which is PV equal to capital N into small k into T. It's not written here, where capital N is number of molecules in the gas, and that small k, it's a constant which is universal for all gases, and that constant is known as not universal gas constant, but Boltzmann constant. Now, number of moles is somewhat proportional to number of gases. So we can replace the capital N by number of moles into Avogadro number. So we can couple that Avogadro number, which is the number of molecules in one mole, into that Boltzmann constant, and we get our universal gas constant R. And small n, which is number of moles. So PV equal to nRT, the classical ideal gas equation. We have that. So ideal gas equation deals basically with the bulk properties, like it treats the matter as some sort of continuum, the gas as a continuum. Of course, ideal gas theory has a lot of deviations that too in sometimes in extreme cases like high temperature pressure, or in case of some gases like hydrogen. But let's not worry about that. Let's deal only in the ideal scenario, which is somewhat practical in our daily engineering applications. Now we have already covered the ideal gas behavior, which deals with the bulk properties. So now let's go into the main stuff, kinetic theory of gases. Let me just give a motivation, a simple motivation. So let's explore the ideas of pressure and temperature. Density, like we can talk about density in an average sense. So we can say like the amount of mass within a fixed volume, like the ratio. We can call that density. But what about pressure and temperature? Like how can we connect it to with a molecular scale and also in a bulk scale? Imagine you have a box filled with particles, randomly moving particles. So each particles move randomly, they collide with each other. Assume the collision is elastic. So due to this collision and rebounding, some sort of force is exerted on the walls of this container, like box. So we can say that the force per unit area is some kind of pressure. Actually, in fact, it is the pressure exerted by the gas according to kinetic uh, theory of gas. Now, temperature. What exactly is temperature? Temperature is some kind of energy level. It's a level of energy that a matter possesses. I mean, heat follows from higher energy level to lower energy level. So, like we can say, heat transfer follows from high temperature to low temperature. So, how can we formulate the essence of temperature? We say that the molecules, as a bulk, due to interaction with each other, have some sort of energy which is known as internal energy. Yes, internal energy. So, we are considering a significant part of internal energy which is constant in all classical processes of gas undergoes, like changing of pressure and temperature, like some sort of atomic and nuclear energy and all. We don't have to care about that. So let's say that's a constant. Along with that, these molecules, they have random motion. They have some sort of kinetic energy. So the average kinetic of energy of a molecule, not only rotational, like motional kinetic energy, like translational kinetic energy, also rotational kinetic energy. This energy is directly proportional to the temperature in Kelvin scale. So we can connect the kinetic energy of each individual molecule in an average sense to the overall temperature of the gas as a bulk. So that's my motivation of how kinetic theory of gases connects bulk properties of ideal gas to molecular nature of a gas. Now let's see the mathematics of this part. So let's discuss about how we model pressure according to the molecular theory. So let's consider a huge cube which encloses a gas. Another special thing about gas is like molecules exhibit random motion. There is no actual static equilibrium. Gas is always dynamic. Gas doesn't have a static nature. So the gas molecules move around here and there, bounce off the walls. So Let's assume two things. One thing is these molecules they bounce elastically, like there is no loss through sound or something. Like these particles are rigid balls, and also the force of attraction between two individual molecules is very negligible, so we can ignore them. And the distance between the gases is very large compared to the molecular size. Like distance between gases means the distance between the molecules in the gases. So I'm taking one wall of this cubical enclosure. I have some sort of a coordinate frame defined over here where the z-axis, the z cap, is normal to this surface or wall I'm considering. As you can see, a green particle is coming and it's bouncing off the wall. Its y and x components of velocity remains unchanged, but the z component of velocity, which is normal to the wall, it becomes negative. It's some sort of flips. So we can have a momentum change, like some sort of impulse. Let's delve into the further derivation of that. So let's get into the modeling of the collision with the ball. I mean, let's take a cylindrical element which is going to impact the wall as shown in the diagram over here. In the cylindrical element, we have capital N number of molecules and small m is the number of like mass of each molecule. Now the dimensions of the cylindrical element are mentioned above. A is the area of cross section and delta L is some sort of the length of the element. Now thing is the average of x and y components of velocity of the particles in the element are some sort of cancelling out of the nature. Since the gas is so random, still the gas is somewhat static as a bulk, static inside the cubical enclosure. So we can assume this element, I mean of course the element will have significant components, like the averaging works in an entire bulk since this is a small element. So for consideration, this element has a velocity vz in the direction of the normal to the wall. So this cylindrical element comes and collides with the wall and reverses its speed entirely due to an elastic collision with the wall. Now let's consider the momentum change or the impulse due to this collision, and this impulse is 2 vz into the mass of all molecules in that element, which is m into n. Now, time taken for this collision is the time taken for the entire element to flip, which is the like the last element. I mean, sorry, the last particle in the element, like the furthest away from the wall, should return back to its initial position just before the collision of the element. So the time taken delta t equal to 2 into delta L by Vz. So one time is to get from delta L to the wall, then collide and go back to delta L. I mean, if we calculate the force due to this impulse, we get Vz square Mn by delta L. So this is the force imparted on the wall due to collision of a small element of gases. So we are taking a cylindrical element without loss of generality. Now I will just convert this force into pressure and some sort of average it to get interesting results. Let's see. So here are some vague mathematical manipulations only. So as I have discussed, the delta F is the small elemental force imparted by the cylindrical element. If we divide it with the area of the cross section, we get some kind of pressure imparted by that element of gas. So we have the expression of the pressure here, and let's take this cursive V as the volume of the element. Since Mn is a small quantity, V by Mn is somewhat kind of a considerable quantity, and we know that volume is directly proportional to the number of molecules and molecular mass in general. So total mass by volume in some sort of density. Since P and T are fixed, so density is constant across the entire volume. So like we can replace V with the bulk volume, this cursive V. Now this, now the underlying issue here is Vz can be anything. We don't know what is Vz. Like how do we find Vz? Now here comes an averaging idea. At different time intervals, the Vz that is impacting this wall is going to be different. And also at different locations, Vz is going to be different. So how to go about this averaging? So let's say uh, all the particles in this gas has some velocity v. If we take average of this velocity, we get zero. Why do we get zero? Because the gas inside the box, like as in the net, is constant. Like not constant, like static. Like it doesn't move. Like gas is not moving as a bulk. So the average velocity of the gas is zero. But here is the thing: the average velocity of the average square of the velocity, like if you take the square of velocity and kind of average it, it's non-zero of course, because the gas is moving, it has some sort of finite non-zero kinetic energy. Now the gas is isotropic, ideal gases are isotropic, all the properties are same in all directions. So we can say that v average of vz square is same as average of vx square, which is same as average of Vy square. And if you add these three same components, we get the average of velocity square. Now, the square root of average of velocity square is some kind of property of a gas. We call that RMS velocity of the gas. Root means square velocity of the gas of each individual particle. Now, Vz square into 3 times equal to V RMS square. So we have Vz square equal to V RMS square by 3. So we can plug that expression into this, and some sort of a kinetic equation of gas is going to be ready. Let's see. So voila, we have our kinetic theory of gas equation. I mean in an averaged out sense. Now I would like to give an intuition about the next part. We are going to talk about temperature and kinetic energy. So like, I mean hand wave intuitive way, we know that temperature is somewhat related to the kinetic energy, average kinetic energy, not average, like net kinetic energy of the uh, gas molecules. And Vrms is like a measure of kinetic energy. Now this we know PV equal to capital N KBRT. Now we are going to plug that into this expression, and we are going to get the kinetic energy in terms of Vrms. Let's check it out. So we have mathematically established that the net kinetic energy of the gas molecule, each gas molecule, and also of the entire bulk is directly proportional to the temperature in Kelvin scale. So we just established relation between both pressure and temperature in the bulk scale to molecular motion, momentum, and kinetic energy in molecular scale. It's quite interesting to note that the kinetic energy is like 3 by 2 kBt. where Kb is the Boltzmann constant. So that 3 by 2. We can assume that our kinetic energy is made up of three components. One is the x component, other is the y component, and z component. Due to isotropic nature, let's into divide the kinetic energy into the three components. So we have half kbt square for motion along the x-axis, half kbt square for motion along the y-axis, half kbt, not t square, half kbt for motion along the z-axis. So motion among x, y, z can be considered as 3 degrees of freedom. Like it's a way in which a molecule can move. And due to isotropic, some sort of averaged out nature, the next thing we are going to discuss is equipartition of energy. So temperature is some sort of energy level, and temperature of a gas determines the amount of energy in it. And the next major assumption we are going to take is it's not an assumption, it's some kind of a theory. It works well. It is the total energy of the gas is equally distributed to each mode of freedom or degree of freedom. So, other than translation, gases can have rotational degrees of freedom. I mean, some degrees of freedom cancel out based on symmetries and all. So, let's talk about all degrees of freedom. One degree of freedom is translation motion, which has like three components. So, 3 kbt square. Now, rotational motion. Suppose our body is not body, sorry, molecule is not symmetric. We have three different principal axes. Principal axes are the axes among which the moment of inertia is maximum. You must have learned about moment of inertia in rigid body dynamics. So among three principal axes, you have 3 degrees of freedom of rotation. So again another 3 kbt. So 3 kbt for translation and 3 kbt for rotation. Then some molecules also have vibration. So another half kbt for the vibrational energy. So that there is known as equipartition of energy, where that like half kbt amount of energy is given to each mode of freedom. Like so, that's equipartition of energy for you, and this is very important in determining how the energy of the gas changes when we adjust the temperature and all, which somewhat leads to the modeling of specific heat capacity for gases in different processes.